let's start. So today we're going to look at Gaussian path integrals. So that's one of the ways how one can try to make sense of path integration. That's of course some very special type, and as we'll see, even there we have some number of difficulties. Maybe one thing I should say, the course is approaching its end, right? And from the very beginning I was saying that sometimes we'll be kind of replacing the proofs with examples, sometimes we'll only be kind of skimming the surface of some proofs. It will be very true today. So, so let me start by recalling how Gaussian integration works in finite dimensions. So let's say V is Rn, and A from V to V is self-adjoint, which means it's a symmetric matrix, and let's say it's positive definite. So this means we can order the eigenvalues say from lambda 1 to lambda n, and we can consider the following n-dimensional integral. Where the scalar product is just the standard scalar product of Rn. Maybe I will add a linear term in the exponential. So, of course, we know how to compute such integrals. We were already discussing it, the one-dimensional case in the steepest descent method, and the general answer is 2 pi to the power n over 2 divided by the determinant of f of a, which is a positive number, to the power 1/2, and here will be what? The exponential of 1/2 y a minus 1 y. By my assumptions, all the eigenvalues are positive. This means the operator is invertible, so a minus 1 is well defined. And that's a beautiful formula for the Gaussian integrals in finite dimensions. Now maybe just a small variation, right? Sometimes we want to put the imaginary unit here in the exponential. Now let's assume that a is still self-adjoint and invertible, so we no longer need to assume it's positive definite. So then we can look at the integral of the form. So now I put the imaginary exponential, and here of course I can put whatever I want, but let's also put the linear term to be pure imaginary. And we looked at the one-dimensional case in the stationary phase, and in a general situation, that's how it's going to look like. So it is 2 pi to the power n over 2. Now we take the square root of the absolute value of the determinant of a. It is non-zero because a is invertible. And here we put exponential of I pi over 4 and plus, minus, and minus. I'll say what it is in a second. And here, that I never remember, it's minus, yeah. Here will be minus I over 2 y a minus 1 y. So here n plus and n minus is a number of positive eigenvalues. Of A. And n minus is a number of negative eigenvalues. So remember, right, we had this story of turning the integration contour by pi over 4. If the eigenvalue is negative, you have to turn it by minus pi over 4. That's where those factors come from.
This integral isn't absolutely convergent.
Sorry?
This integral isn't absolutely convergent.
This integral isn't absolutely convergent.
This is like in principle.
Yeah, that's right. Oh, that's similar to what we had in the one-dimensional case, right? You have that integral over the complex domain, and then you kind of show that you can turn the contour. That's right. So then you send your limit to infinity, and you get an answer. But of course, it's obviously not absolutely convergent, because if you take an absolute value, right, it's just 1. That's right. So here is a small remark. So in principle, you can view both these formulas as one formula, right? So in order to do that, you need to put an operator to be, instead of self-adjoint, anti-self-adjoint. And then basically the only thing that you need to decide is what to do with the determinant, right? So in the determinant, you will have some square roots of I or of minus I, right? If you do that. So so it's essentially the same algebraic formula. And you have a convention that the square root of I and minus I have positive real part. So that's these are essentially the square roots of I and minus I that you are counting here. So so here is our goal for today. We would like to make sense, at least in some cases. Let me choose perhaps this form, but doesn't matter so much. Over the space V, which is now not necessarily finite dimensional, right? That's why I write this thing here. In principle, there would be not much of a hope to make sense of the factors like 2 pi to the power n over 2. Remember, we had some infinite factors already last time in front of our path integral. Let's be vague about it. One can be somewhat more precise, but let me put some constant there. But what is essential for us is to make sense of the exponential factor and of the determinant. Of course, we will have to have some assumptions on the operator A, and we have to discuss what the right-hand side means. probably one should say, we're not going to be discuss much the exponential factor. So this essentially doesn't pose much of a problem. Of course, A needs to be invertible, right? So you need some kind of reasonable inverse, but usually this is not much of a problem. We'll look at examples, and this will not be a big problem. The main topic of the discussion today is this term. So what are the assumptions on A, and what is the determinant of A? So, so basically that's the main topic. So what do we do with the determinant of A? And note that now this formula becomes a definition of the left-hand side. So here, of course, those formulas we prove. We compute and we obtain the answer. So that's essentially the definition of Gaussian path integrals. Okay. So let's make some assumptions on A. So I will think that our operators act on a separable Hilbert space. So as usual, now we'll be assuming that A has a Hilbert basis of eigenvectors. So then, so I'll be introducing those assumptions. I will add up assumptions when needed. So I'll assume that A is bounded from below and may have some finite number of negative eigenvalues, but other eigenvalues, the infinity of eigenvalues, are positive. So lambdas will be sufficiently rapidly growing with k, so we'll now make it somewhat more precise, and then maybe we'll have further assumptions on the growth rate. So of course, such an operator is invertible, right? So there is this Hilbert basis. There is no eigenvalue equal to 0, so A minus 1 is simply defined on a basis by this formula. And we assume that the sum of inverse eigenvalues is absolutely convergent. So that's one of the assumptions. Of course, for that, lambdas should grow sufficiently rapidly. All right. So there are many constructions for determinants of infinite dimensional operators on the market. And we will be talking today about two constructions, not in full generality, but in application to this setup. And the first construction is called Fredholm determinant. So let me first look at the following finite dimensional situation, and then the infinite dimensional one. So let me write the following obvious finite dimensional formulas. So the determinant of 1 minus A inverse, right? Well, this is simply a product let's say our dimension is some capital N. So this is simply the product of eigenvalues. And eigenvalues are simply 1 minus lambda k inverse. Maybe a somewhat more interesting determinant. Let's introduce a variable lambda. So such a determinant will be given by this formula. Now, let's assume that we are in the infinite dimensional setup. Then it turns out we can still use those formulas. So the corresponding determinant is called the Fredholm determinant. Well, it is given by an infinite product. And this infinite product, under the assumption that the sum of inverse eigenvalues is absolutely convergent, so this infinite product is convergent. That is, I take finite products, this gives me sequence, and this sequence converges. Now, of course, in a very similar fashion, we can add the parameter lambda. If we multiply or if we divide all lambda k's by lambda, of course, this series is still absolutely convergent. They're just multiplying it by some number. So we obtain an infinite product, which is now depends on lambda. So this infinite product defines a holomorphic function with zeros exactly at lambda equal to lambda k's. So where one of the factors vanishes. So from this perspective, this Fredholm determinant behaves in a fashion that we expect of the determinant of such an operator. So I'll give you, I don't promise many examples, but I'll give you at least one example in some minutes from now. But before doing that, let's look at a different construction of the determinant. Which is called a Zeta-regularized So the Zeta-regularized determinant. So maybe again, let's start with a finite dimensional situation. So here the idea is as follows. Let's define a function of complex variable s, so zeta a of s, by the following formula. So now I assume that all the eigenvalues are positive. So this will be sum from 1 to n (1 over lambda k to the s). Or I can rewrite it in this form. So the sum of exponential functions of minus s times logarithm of lambda k. Now this is a holomorphic function of s on the whole complex plane, and in particular I can look at its value at 0, right? So the value at 0 is simply the sum of ones, and this is equal to n, and this is the dimension of the space V. Now, somewhat more interestingly, let's look at the derivative of zeta at 0. So this will be minus the sum from 1 to n of logs of lambda k. And this formula implies that if I take exponential of minus the derivative of zeta at 0, so this will be product of lambda k's, and this will be the determinant of A. Right. So now let's look at the infinite dimensional situation. So there we can also look at a similar definition. Let's again assume for a moment that all the eigenvalues are positive. So now we're getting an infinite series. And this infinite series defines a holomorphic function, but now possibly not everywhere, right? So for sure our assumptions apply that if the real part of S is greater than something, for instance, if it is greater than 1, then we are good, right? Because at 1 already we had absolute convergence, and probably even to the left of that line. Now let's assume that zeta A of S admits an analytic continuation to some open neighborhood of 0. So then we declare delta A its value at 0 to be the dimension of V with respect to A, right? So now V is infinite dimensional, so it doesn't have any reasonable dimension, but delta A by assumption is some number. So we now say it is our dimension, and we define the Zeta-regularized determinant of A by definition as an exponential of the derivative of zeta at 0. Of course, just by that formula. Let me state one proposition with a proof, one theorem, probably without proof, and then we'll finally look at an example. Maybe one more remark about this definition. So a priori, with this formula, I defined my determinant only for operators with positive eigenvalues. But if you have a finite number of negative eigenvalues, this is also not a problem. So suppose that the first small n eigenvalues are positive and are negative and the remaining are positive. Then we can define an operator with positive eigenvalues which only acts on the space spanned by the basis vectors with k greater or equal than n plus 1, right? So then you can define the Zeta-regularized determinant of A as a product from 1 to n of the negative eigenvalues. And for the rest of it, you take a Zeta-regularized determinant of the operator acting with positive eigenvalues on the remaining part. So this is just to fix the notation. Now a proposition. Suppose that I take a positive real number and I consider the Zeta-regularized determinant of this positive number times A. Of course, C times A is an operator with similar properties. So then at least for positive eigenvalues, that's what we get. We get C to the power delta A, and we get this Zeta-regularized determinant of A. Now here is the proof. So by definition, right, we need to consider zeta prime of CA at 0, right? So so this is d over ds. And so what happens with zeta, right? When I multiply all the eigenvalues by c, I get a factor c to the power minus s, and here will be zeta a of s at s equals 0, right? So what does it give me? So this gives minus log of c times zeta a of 0 plus zeta a prime of 0, right? So, and this means that the zeta determinant of CA, this is x of minus zeta prime of CA of 0. And then the first term gives me C to the power zeta A of 0. And the second term gives me the determinant, right? Okay. Now here is a theorem that's important for us, but we're not going to prove it. So this is a relation between the Zeta-regularized determinant and the Fredholm determinant. So we're going to look at the characteristic determinant, A of A minus lambda. It's zeta-regularized. Of course, we now assume that lambda is not an eigenvalue, even though it's relatively easy to extend the definition, right? If one of the lambdas is 0, well, the determinant, the zeta-regularized determinant, is any determinant is 0. So is equal to the zeta-regularized determinant of A times the Fredholm determinant of 1 minus lambda A inverse. So that's again something that you would expect from the determinants. The only thing is, right, here the determinant is defined in a more or less natural, naive way as an infinite product, and it makes sense. But here you cannot define it as an infinite product of eigenvalues because it's wildly diverging. So that's why you define it using this zeta function procedure, and then still everything matches. So that this means that our definitions of determinants, they kind of make sense. Well, maybe now an example. So we'll consider the operator which probably appears most often in this course. So minus the second derivative. And as a domain, I'll take C2 functions on the segment of length small t. And I'll put here a condition 0, which means that, so I consider functions psi of x and psi of 0 is equal to psi of t is equal to 0, or usually it's called Dirichlet boundary conditions. So this operator is essentially self-adjoint, and there is a Hilbert basis of eigenvectors. So eigenvectors, let me call them psi k of x. I will not be normalizing them, but if you want, you can normalize them. So these are sine functions of pi k over t. And the corresponding eigenvalues, they will be simply pi k over t squared. Right. Okay. So maybe we start with Fredholm determinant of 1 minus lambda a minus 1. Of course, this a is invertible, right? By the way, maybe a test question. So how do you write the inverse? So just to check whether we still remember the Wednesday class.
Inverse of a minus 1?
No, inverse of a.
Just
Maybe use it Fourier.
Fourier, yeah, sure. Something better than Fourier, or something
spectral function.
easier than Fourier. So maybe I just recall that last time at the exercises we looked at inverses of such operators and their integral operators, with some nice kernels. So this would be an integral operator with some kind of exponential kernel. So just, all right. So what is this determinant, right? So that's a product, an infinite product, and here we should put 1 minus t over pi square, and here lambda over k square. So do you know what's the value of this infinite product? Right? So this is an entire function of lambda, a holomorphic function on the complex plane. What is this function? Right? That's one of the standard facts from complex analysis.
Sine.
Yeah. Sine sounds good. Sine of what?
Lambda t. Square root of lambda.
Yeah. So so I would say right. Could it be true for the sine function? No pi, right? No pi. Yeah, but this guy would also have. First of all, it's not very entire, right? It has the square root, and second of all, it has 0 at lambda equals 0. So this should be remedied in some way. So I think divided by t square root of lambda. Is it correct? I think this is now an entire function of lambda, right? Square roots are gone. And also it has zeros exactly when lambda is equal to pi over t squared times k squared. Right. Okay, so that's simply the answer for this Fredholm determinant. Now let's look at the Zeta-regularized. Zeta-regularized determinant. So then, so zeta A of S is equal to what? It's so how is it? It is C over pi. Is it correct? I'm always, yeah, to the power 2s, and then sum over k from 1 to infinity, 1 over k to the power 2s. Now this function is up to this multiple of 2 is the original Riemann zeta function. So this is equal to t over pi 2s zeta of 2s, where this is the Riemann zeta function. So let me recall, or let me tell you, that the Riemann zeta function, so zeta of s, is actually meromorphic on the whole complex plane. It has the unique pole at s equal 1. And this pole corresponds to the harmonic series, sum of 1 over k. And what is interesting for us are the values of zeta of 0, which is minus 1/2. And zeta prime of 0 is minus 1/2 times log of 2 pi. So, so these are the complex analysis facts about the Riemann zeta function, or elementary facts. So now we can look at our example. So we want to know what is zeta a of 0, right? So here we just get 1, here we get 0, so this is actually minus 1/2. That's a kind of funny thing, right? That's the dimension or effective dimension of our space, of our Hilbert space. It turns out to be negative and equal to minus 1/2 according to that definition. And zeta prime of 0. So how is it? What will it be? So this will be 2 logarithm of t over pi plus what? Plus 2 derivatives, right? Minus 1/2 log 2 pi. Is it correct? No, I think here times the value at 0, right? Times minus 1/2. So this gives us minus log t over pi minus log 2 pi and is equal to minus log 2t. So the conclusion, the zeta-regularized determinant of A is equal to exponential of minus log 2t. So this is equal to 2t. And finally, from these two formulas, we get the zeta-regularized characteristic determinant, A minus lambda. So this is equal to the product of these two expressions. And this is twice sine of t square root of lambda divided by the square root of lambda. Well, so that's an interesting expression. We're going to make use of it later on, but it shows a little bit how those infinite dimensional determinants work. So let's have a break, and after the break we're going to apply our determinant machinery to computing actual Gaussian path integrals. All right, let's continue. Now, during this hour, we will consider an application of the Gaussian path integral formalism, and this application will be an asymptotic of the propagator of the Schrödinger equation for h bar small. So this is a quasi-classical asymptotic behavior similar to what we looked at before in the WKB, so the same type of expressions. And for that, probably I should recall the formula that we obtained last time. So, so that's the formula for the propagator, which gives it as a constant times the Feynman path integral over trajectories. Or maybe S. Let me call it S. So the path integral over trajectories, and here the exponential of the functional, which is called the classical action. And this classical action is given by formula which depends on time which enters the propagator. So this propagator is for the time t, and here we have m over 2. How did we denote it? X dot or x prime? Maybe I denoted x prime. X dot, okay, sorry. Right, so that's the expression for the classical action function. As we said before, a priori, this symbol has a meaning of the limit that we wrote last time, but as an integral over some measure, it doesn't have such an interpretation. So now we'll attempt to approximate it by a Gaussian integral. So first of all, let's look at this expression s of x. And yeah, here I should probably add that we are looking at trajectories which start at the point y and which end at the point x. And these are the two arguments of the propagator. So let's do the following. Let's say x of s. This is some fixed trajectory, x naught of s, plus an extra term, u of s. And we'll assume that x naught is an allowed trajectory, so it satisfies, it has the correct boundary values. And then u vanishes at the endpoints of the segment 0t. Now let's just make a substitution of this sum into the expression for the action. And let's assume that the potential V is nice, for instance, real analytic, and we can use the Taylor expansion for that potential. Let's assume that the Taylor series simply converges. It doesn't matter so much, but or maybe let me go to the other blackboard. So what do we get? Let's group the terms in the following way. So I start with a term where I simply pick the terms which only contain x naught and which do not contain u. So this is the zeroth term of the Taylor expansion for the function v. Now, so let me write down the next term. So this will be a linear term in u. And let me write it in the following way. plus v prime So let me write it like this. So what happened? So first of all, so that's the first term in the Taylor expansion, right? So the derivative times u for the function v of x. And here what happened, a priori here I was supposed to get x naught dot times u dot. But then I integrated by parts and I used the fact that u vanishes at the endpoints of the interval. So this means that there is no extra integral term, and here I have u double dot instead. So that's the result of the integration by parts. So that's, so actually, this coefficient is also called the functional or Fréchet derivative of the functional s with respect to the argument x. Maybe with a minus sign because I collected a minus sign here. So, all right, let's continue. Let me write the next term as follows. Minus 1/2 integral 0 to t u of s, and here let me write it as follows. So this is m u double prime of s plus v double prime of x naught of s u of s. Sorry. No, this guy, right? Yeah, maybe you should watch my hands, right? I hope that's the correct next term. So this is a quadratic term in u, and then a priori there will be further terms, right? V may be complicated, but let's stop here. So then there is something which is at least cubic in u. So that's the expression that we get. And the idea of the asymptotic is to simply forget this term. So we'll be replacing the supposedly exact expression for kt by some expression which is not exact, and then we will be discussing that other expression. So first of all, a little bit about terminology. So here this minus ds over dx, this coefficient in front of the linear term, mu double dot of s plus v prime of x naught of s. So the terminology is as follows. If x naught satisfies, sorry, what am I, no. Oh, my apologies. So it's all wrong, right? Okay. Now hopefully it's a little bit more correct. Could it be? Yeah, the first term was completely screwed up. Who knows, maybe I did it on purpose. Nobody pays attention. All right, so if this first term is equal to 0, so then x naught is called a classical trajectory, and sometimes denoted x classical of S. And note that this equation is actually something that we know from high school. That's the so that's the second Newton's law, or the equation of motion for a classical system that we already saw in the WKB approximation. So it defines for us a dynamical system, and so that's the law for the classical motion. So that comes from classical mechanics. So let's make an assumption, a simplifying assumption. Assume that for all pairs of points x, y, and for all time periods t greater than 0, there is a unique classical trajectory. Right? Because in principle, and this does happen, we can imagine that there are many solutions to this equation which start at y and at x in time t, right? But now let's assume that there is always only one. So this is an assumption about the system. So then let's define a quasi-classical propagator, kt. Again, as an integral over trajectories. Here we again put the same conditions: x of 0 equal to y, x of t equal to x. And here, let's do the following. Let me introduce the notation. Say that this first term is S0, the second term is S1, and the third term is S2. And here, instead of the action functional, I simply write down the sum of those three terms. So this is still not quite a definition that I have in mind. So let me continue. And note that this equality is still some kind of shaky equality. So I would like to make a substitution here, the substitution that I had before. X is equal to x classical plus u. And I would like to rewrite this expression as an integral over du. And here, well, so there will be S0 of x classical, right? Because it's only x naught which enters S0. Now, if I substituted x classical, S1 will be vanishing, right? So actually, x classical is exactly the solution of the equation that this expression is 0, right? And then there will be S2, which depends on x classical and on U. Note that, right, we said there is no such a measure. So here I'm assuming that this measure is a kind of translation invariant, but such measures do not exist. So basically, that's the true definition. So this is kind of not a true definition. Now, this expression is of the kind that we were discussing before. This is a Gaussian path integral, right? So this is simply constant. It doesn't depend on any u. And this expression is actually an expression of interest for us. So this is a quadratic expression in U, and here we have some linear operator. Now we'll have to discuss what kind of linear operator is there. All right. So a priori, the answer should be a constant times S naught of x classical. And here we'll have a priori the determinant of some operator a to the power minus 1/2. Now we can say that we want the determinants that we know. These are zeta-regularized determinants. So is zeta-regularized determinant of the operator a, and what is the operator a? So a of u is equal to minus MOH bar d2 over ds square u minus 1 over h bar v double prime of x classical of s u of s. So that's the operator. I hope I got the signs correctly. Probably times I somewhere. Right. And u of 0 equal to u of t is equal to 0. So that's the operator that we're getting. So let's look at an example. And then let's discuss a little bit the general case. Well, as you can imagine, what is my favorite example? That's the free particle, right? And v equal to 0. Well, in this case, our operator A is this, or S, sorry. Now I kind of renamed the variable. So we won't be too much attempting to think about the constants, but so we know that the zeta-regularized determinant of A. Recall that for the operator minus d2 over ds squared, it was equal to 2t. right? Now there will be some constant coming from the rescaling. Let me, since in the end anyways we will not be taking into account all the constants correctly, let me put it in this relatively vague way. So there is a constant times the time t. So this implies kt quasi is equal to a constant. Now we know that we should put 1 over square root of t. And now let's compute what happens with S naught of x classical. Now the classical equations of motion for the free particle is simply mx double dot of s equal to 0. So x of s is equal to a plus bs. Well, we impose the conditions that x classical of 0 is y, x classical of t is x. So then this implies x of s is equal to what? Y plus x minus y over t times s, right? So now we're kind of back to the elementary school. And s of x classical is integral from 0 to t m over 2x classical dot squared. There is no potential. X dot is x minus y over t. So all in all, it is m over 2 x minus y over t squared times t. And the value is m over 2 x minus y squared over t. So finally, we can now write down the answer. And this answer is exponential im over 2 h bar t times x minus y squared. So that's the quasi-classical answer that we obtain up to some coefficient. And perhaps you can recall what's the true answer. Someone can tell me what's the, I think, is it something like this? Could it be? Hmm? Oh. Yeah. Okay. So as I said, up to this constant, we did obtain all the dependencies in the quasi-classical regime correctly. And of course, the free particle is a particularly simple case, but still, well, it's interesting, right? So one thing was an exact computation for the for the Schrödinger equation. We solved our Schrödinger equation and we obtained the exact result. Now we use this very different technique. We had this funny story of the path integral which doesn't quite work, and then we replaced it by an approximate path integral, and then we defined those approximate path integrals with the zeta function regularization of determinants, and the results kind of match. So here it's a very, very satisfactory situation as far as path integrals go. So now maybe let me spend the remaining 20 minutes by discussing a more general situation. So I'll state some results without proof, and for one of the results I will give you a scenario of a proof, and actually this scenario is implemented in the problem set 13. So actually you will do the proof. Right. So so in the general case, assuming again that the potential is sufficiently nice, and assuming again that the uniqueness of the classical trajectory. So theorem. So this kt quasi of xy, it is defined as a Feynman path integral, right? By Gaussian So now I write down the coefficient, and then so I suggest maybe I write down the answer and then give a comment. So you see what happens here. So we assume that there is a unique classical trajectory. Let's imagine that this is t. This is our space coordinate. So here there is t or maybe s. So s equals 0 and s equals t. Now there is an initial point, so the point y, and here there is a final point, the point x. So we assume that there is a unique classical trajectory which goes in time t from x to y. I don't know, something like this, right? So this is x classical of s. Now, similar to this calculation here, we compute S classical on that trajectory. Well, now a priori it now becomes a function of t, x, and y, right? In particular, if we fix t, we can move those points x and y. For instance, I can go like this. And here there will be some other classical trajectory, maybe like that. I don't know. On that classical trajectory, there will be again a classical action. So this classical action is a priori a non-trivial function of x, y, and t, similar to this expression, right? So this expression, for instance, here is a function of x, y, and t, and so this prefactor, I claim that this prefactor is the second derivative. So this zeta-regularized determinant is actually 1 over the second derivative of the classical action over x and y. So that's a kind of interesting and highly non-trivial statement. Maybe an example, right? So again, for the free particle, d2s classical over dx dy, well, we can compute it, right? So it will be minus m over t, if I'm not mistaken, right? And the absolute value will be m over t. So we are neglecting the constants, and then we correctly get 1 over the square root of t that we were getting here. This time we even get correctly the whole thing, right? So the square root of m will combine with this expression to get the right formula. Okay. So one more theorem. Kt of xy, and that's similar to the WKB. So the quasi-classical formula is an asymptotic approximation of the correct true formula when h bar goes to 0. So, so basically that's a kind of upgrade or time-dependent version of WKB story that we looked at before. Now, so this theorem we're not going to prove, but this theorem you will be proving with some effort, possibly, at the next exercise session. And let me describe this scenario, how it actually works. Because the scenario is kind of interesting, and perhaps it would be useful in doing the problem set. So these are some ideas of proof. And this is for this theorem. So the proof consists of several steps. And so step number 1 is like this. So we consider an operator A which is the standard Schrödinger type operator, minus d2 over ds squared plus u of s. It acts on the domain that we now like. So we have a segment from 0 to t, C2 functions with Dirichlet boundary conditions. So let me denote by u the function. So this operator is essentially self-adjoint. And the claim, so that's not part of you're going to prove, is that it has again a Hilbert basis of eigenvectors, and eigenvalues will be like this. So there will be perhaps some constant shift coming from the average of the potential u, but otherwise they will look as operators or as eigenvalues of this operator plus some asymptotically small corrections. And this implies that the determinants that we are interested in are well defined. So the determinant machinery works actually fine. Now an interesting second step. So we know that the equation a minus lambda u equals 0 actually has two linearly independent solutions for any lambda, right? No matter what. Now, in particular, we can choose a solution. Let's call it u1 with the following boundary conditions. You see, so possibly these solutions violate the boundary conditions, right? There are two solutions, but not satisfying boundary conditions in general. Let's look at it as a Cauchy problem. So we fix the value 0 at 0 and the derivative at 0 equal 1. So then you can always solve this equation. Is potential u is nice enough, so there is a solution. Now let's look at this solution at the point t. And we're going to look at it as a function of lambda. So we change lambda, the solution changes, and we obtain this function u1 t of lambda. Now, what does it mean that this operator actually has an eigenvalue with given boundary conditions? Well, this means that this solution u1, it actually vanishes at t, right? So it is equal to 0 if and only if lambda is lambda k for some k, because that's exactly where then in this case u1 becomes an eigenfunction. Now, so this is kind of suggestive. So there is a function of lambda which vanishes exactly at the eigenvalues. So does it remind you of something? What could it be? So one interesting guess, and it turns out to be correct, that as usual in our business up to a constant, the Zeta-regularized determinant turns out to be equal to that value of the solution. Of course, you can also run it from t to 0. So you can define a solution u2, which will be vanishing at t and have some non-trivial derivative, run it back to 0, and then this would be a value of that function at 0. So it doesn't matter. But that's one thing to argue, to prove, to discuss. So this will be one thing to prove that actually this is true. So this is plausible because they are both holomorphic functions. It turns out that this thing is holomorphic in lambda. They vanish at the same points. Of course, they might be still an entire function which is everywhere non-vanishing as a factor, but it turns out that it's just a constant. So this part is a series of determinants. Now, so there is one more part, which is variational calculus. So let's do the following. So we have our classical trajectory, and we can consider, let me call it u naught of s, which is just derivative on the classical trajectory. Well, this is some function, and it turns out that u naught is an element of the kernel of A. Again, no boundary conditions respected, right? Just viewed as a differential equation. As an ordinary differential equation. It doesn't satisfy any reasonable boundary conditions. Well, but now, you know, once you have two solutions of the same equation with possibly different boundary conditions, remember we had some problems in that direction. This means you can express the other solution in terms of the first one. So right, so there should be some expression. So we know two solutions, they always know each other. So u1 in particular, u1 of t naught should be expressible in terms of u naught. Now we have the classical action, and we want to study the classical action as a function of x and y. Well, now it's an exercise in the variational calculus. Of course, it's expressed in terms of classical trajectory, and in particular, it turns out you can write it down in terms of u naught. Miraculously, these two expressions coincide. Right? So this thing is expressed in some way as a function of u naught. This thing is also expressed as a function of u naught. It turns out these are the same functions, and a priori, right, if you believe all that, this concludes the proof. So the determinant is proportional to u1. u1 turns out to be expressible in terms of more or less equal to the second derivative of the action, maybe up to sine or maybe up to constant. And so that's the scenario for proving the theorem. So you can try it yourself. If not, we'll do it next Monday with the problem set 13. So that's the right. Well, so that's it for today. And next time we're gonna look at the path integrals from a very different perspective. So this was a little bit of a story. So those Gaussian path integrals. So we were using essentially techniques from the theory of infinite-dimensional determinants, and also we continued using the language of differential equations. And next time we'll briefly dive into the probability theory, and we'll try to honestly define path integrals. So the finest path integral, as I said, it's impossible, but we'll still see what people could come up with and what one can define as real integrals over infinite dimensional spaces with well-defined measures. So that will be the program for the last class. All right. So thanks.